Welcome, everyone. Thank you for joining us. Before we start, I want to give a big shout out to Yelp for hosting us again in this beautiful space and providing us food. I hope you guys helped yourself to pizza. I see some of you helped yourself to beer. That's good. um, so, a little bit about this meetup. This is the ACM SF meetup. If this doesn't look familiar to you, then you're probably at the wrong place. Um, my name is Abhilash Jindal. I am CTO of Mobile Analytics. I work right across the street at a co-working space called Workwise. We build energy debugging solutions for mobile apps. Here I have with me Ria. She works at the data streams team at Yelp for the last 3 years. If you're not familiar with ACM, ACM is a non-profit organization that brings together computer researchers, students, practitioners to talk about cutting edge things that are happening in computer science, such as the two talks we have today. So without further ado, I'll introduce Luca, who is going to talk about real-time store visit predictions at scale. Luca works as a software engineer on the core ML team at Yelp. While part of his job involves data mining massive data sets at Yelp, he's also responsible for designing and scaling the backend for analyzing high volume geospatial data of Yelp's mobile users. He was previously the main open source contributor to Yelp's asynchronous client Fido. Let's welcome Luca.
Thank you, Abdullah. All right. This is Luca, and I'm in core machine learning. We build infrastructure for all the teams at Yelp for them to build machine learning models. So we support them, we mentor them, and we build ML infra. And today, yes, I speak about real-time store visit predictions at scale, which is how we implemented model serving in a stream processing job. So what can you expect from this? I'd like to introduce, first of all, the product that we power with this system so that you can keep in touch with what we're talking about. And we'll go through the logic and the algorithm in abstract. And then I'd like to introduce you to a bleeding edge stream processing framework that is called Flink. So that's what we used. And so I will talk about how we implemented this logic in Flink. Finally, a few words about the impact that the adopting Flink had on our team and on the project. So, few words of introduction for Yelp. Yelp mission is to connect people with great local businesses. And in order to do so, we always come up with new product and features. One of these was a new type of push notification. That is the one you see in this picture. This is one of the best performing push notifications at Yelp. And I don't know if you can read. The aim of this notification is to suggest the best nearby business to Yelp users. So the one in this example is a notification that I got, and it's suggesting a burger place creator nearby. And as a matter of fact, I was there. So this is the best case scenario is to notify users, be relevant and timely with this notification, right? So we don't want the notification to come too late. We want to provide all the information from the Yelp app, menus, reviews, pictures, just one click away when you are actually at the business. And it needs to be relevant. So it needs to be, so we built a machine learning model to choose the best business nearby for a specific user based on user and business features.
What do you mean by the best performing push notification?
So this is one of the best performing in the sense that it is the first or the second that people like to click. Like when people see it, the click-through rate is the highest. So it gets clicked on. because generally it's very relevant. I'm the first one to be very curious because generally it's something that I know is either nearby or is the place where I'm actually at. So it's followed by a surprise, at least for me. Yeah, and a few words. So whoever wants to opt in can easily share the location in the Yelp app, but whoever wants to keep a lower profile can just as easily deactivate the location sharing in the Yelp app. So, all right. So I'd like you to explain to you how we solve this problem. And we'll start from the data that we had. This we call these raw pings. They represent coordinates, latitude and longitude on map. This is my own data. These are instantaneous locations, so we can't really use them as is. The first thing that we want to do is to detect when someone is stopped somewhere, when they're visiting somewhere. So all the stopovers or visits. So the first step of our algorithm will be to cluster pings together, the ones that are close in time and space. And in this example, we get a visit that is enclosed in the blue circle. So I was more or less there. And the next step will be to retrieve a list of candidate nearby businesses. Candidate in the sense, one of them is probably where I'm going or is the best fit for me. As you can see, there's Creator, Trader Joe's, a hospital, so there's a few of them. And now we have a list of them, but we don't know yet which one is the best one. So at this point, the ML model comes into place. It's an XGBoost model, and it takes as input the user and the location, so Luca at a certain intersection, and given a candidate, a list of candidate businesses, it will sort them and get the best one for this situation. System overview to have an idea of how the system looks like. To the left, you can see the input data, which is thousands of pings per second, raw pings, so instantaneous locations, coming via the Yelp data pipeline into the Flink job. Here, we perform the clustering that you saw before, and we delegate the machine learning to an external Python service, and we use Flink on async IO interface to perform efficient asynchronous calls to this service. The inference happens here. We get the results back. So we get the predicted business back. We call it store. And then we assign such store to our visits. And we create an enhanced object that we call store visit. We put this back into the data pipeline so that other teams downstream can use the data. And about the clustering itself, a long time ago, we performed a few data analysis, trying a few different clustering algorithms, but we soon understood that it was very hard for us to use very complex clustering algorithms because they generally require a lot of pings, and one of the requirements was low latency, as we saw before, because the notification has to arrive quickly. So we had to use a fewer number of pings, and so we started analyzing some heuristic rules, and we found out that generally we get very good recall by using only 2 pings. In this example, we tried setting different thresholds and in time and space, and we found out that a couple of pings are enough to detect if someone is stopped somewhere. And you can see as soon as we detect that, we emit an arrival visit object, which has a starting time for that visit at 3:21 and a departure time that is yet unknown. This is modeled on Apple Visit Library, so they provide this, and they provide this already with the library, and we basically replicated this in Android in the backend system. when we get another ping that is close to the previous ones, if it's close enough, we make it part of the same visit. When it's further than d meters, so than our specific threshold, we can be reasonably sure the user has left, and we close the previous visit, so we emit an object that is called departure visit, and we have a departure time now, which is 3:30 in this example. Yeah, and we label the new one. It's probably going to be a transit ping in this case, but it could also be the start of a new visit. So all this was implemented into Flink's own process window function, which is an interface where you can write your own processing function over the data that you're getting in a stream. And here is an example with a few more pings, and I'm introducing another Flink own construct, which is the global window. The global window is a global window contains the pings in input. We decided to assign a global window to each user, so this processing can be easily parallelized because each global window can be run on in different processes, even different machines. So Flink provides scaling in this fashion. It's really great. And in this example, we run through the same pings as before, and you can see that there's a new visit, the yellow one here, and as soon as we proceed, the window always sees only 2 pings because we decided that 2 were enough. So we keep removing old pings from this window and adding the new ones when they come in. And this window is like, it's sliding on pair of pings. So it's not time-based, but it's more event-based. As soon as a ping arrives, the window changes its content. And yeah, so another Flink interface. This component, we implemented our own custom trigger. The trigger is the component that makes the decision of when to run your clustering, your processing, whatever your processing is. In our case, it's our simple clustering. And we called it on any ping trigger, which means we decided to run the clustering anytime we receive a ping, because that was enough for us. And we also needed a way to remove pings from the window, because that doesn't happen automatically. I mean, it can be based on different rules. And we went for a default Flink counter victor, which is a way to tell Flink, hey, only keep this amount of pings into your window. In our case, we said we always wanted 2. And so as soon as we have 2, the older one gets removed. I mean, we said 1, I think, and it gets removed. And then we get a new one, and we get 2, and we run processing. So you can do it either way. Yeah. Now, the fun part was the issues we ran through, because here it was our first time to deal with stream processing job, which is very different than dealing with batch jobs, and the concept of time is different in particular. So here you can see there's 2 times. There's even more, but let's talk about these 2 times right here. We have the event time and processing time. Event time is the time when events are created. So you can see event time as chronological, as the event chronologically happened. While processing time is when the server saw the events, which doesn't mean that they will be seen in a chronological order. They could be out of order when they get to your backend system. Imagine our events are created on mobiles, which are very, very far from the backend, and so many things can happen between mobile and various backend systems. So mobiles can go offline for long periods of time, and you get no data in that period, in that time frame, and their clocks can be completely off. So you don't have the synchronous clock like you might have on servers. So what happens here is we were having so many messages coming out of order. Also, our backend system, sometimes you might distribute your traffic horizontally, and in some parts of your pipeline, you might not get guarantees on ordering of messages. So that also plays a role. So yeah, how do we, so this is very different than a batch. A batch generally runs, at least at Yelp, it generally run over the previous day of data. So you wait a day, you wait, the entire data has had time to come in, and you generally run your select query, you order by, and you get all the data in order. So it's, for us, it's different. We have a window that is not a day, but is a few, it's very small. It only sees 2 pings, not the entire previous day. And we didn't have time to wait more. And yeah, so we don't know, we're not waiting. And so there's a trade-off between correctness and latency. And we wanted latency. And so we had to trade correctness for that. You can think of a batch, the batch world as a specific case than a streaming world, because you could select in your Flink, you could specify a 1-day window and wait for a day for all data to come in, and then sort the data when you process it. So it's like running a batch, but you're defining the same in a streaming paradigm. So it's pretty similar. So what do we do to fix this? Here you can see we have 2 pings. This time I specified both processing time and event time. The first ping is created at 3:21 in event time, but is seen by our servers at 3:22. The second ping is seen by our servers afterwards at 3:24, but it was created, so the timestamp inside of its creation is at 3:10, so it's way before than the green ping. That means it's definitely out of order. We know that based on event time. We decided to drop it. We dropped everything. We didn't wait for any time for late pings. So we could have decided to wait 11 minutes to put an allowed lateness of 11 minutes. In this case, and it would have fixed this case, but we didn't want to wait this 11 minutes to process. So we just acted as if allowed lateness was 0. And the outcome is the one in this picture. You get, our window will only ever see the 2 green pings. The red one is dropped and it's never processed. All right, to the model. A few words about this. We had to save all our features in an online data store to be retrieved in a fast manner, and that was Elasticsearch. So the model is, so we have one feature row for each candidate business, and our model will run over all these rows and will produce a confidence score. We produce a prediction between 0 and 1 for each one of these rows, for each one of these businesses. And the one with the highest one will be the one that we pick. In this case, Creator as it's just an example, but it's 0.99, and we pick this one. And an idea of some features that we use, just to give you an idea of how it works, is here I show you distance and directions. So generally, if a user has asked for directions in a Yelp app, which is when you click them up and you're shown how to get there, that is a pretty significant signal. It means you probably want to go there. And so if you have done that out of the 300 businesses that you have around you, the model will take that into account. It might be that, yeah, you're there or you're going there. And distance is very similar. So these were 2 very meaningful features for our model, and yeah, wanted to show it to you. All right, so a little bit about why Flink was such a great improvement over our previous system. I'll spend just a few seconds on our origin story, what we had before and why we changed. We were using Amazon SQS, which is an Amazon service that provides the consumer-producer paradigm, where you produce a message and consume a message. There's no way to see multiple messages at a time. You always see one. And we needed some kind of state. We needed to know, was this user somewhere before? Was it stopped? Was it moving? Was it, I don't know. We needed this concept of state that Flink gave us. So we had to build our own fragile in-house state using external data stores. That's pretty much what we were doing at Yelp when we use SQS. We generally use Cassandra for this. It was very fragile, and we didn't have that clustering that you saw. We had a worse one. So that is simple. We had one that was even simpler and worse. And we were using a Python layer on top of SQS. and we couldn't be concurrent because it wasn't Python. It's very hard to be concurrent in Python, so it was very hard to scale unless we increase the number of processes. And then SQS is an at least once guarantee, which led to duplicate pushes, because if you get the same message in your queue system twice, then we saw that users were getting the same exact push twice at the same instant, and that's very bad user experience. So what was the impact of moving away from that? First of all, new algorithm, 10 times more visits. That was a huge increase for us. More visits, much more notifications, much better experience. We finally could implement machine learning predictions. Before we didn't even have this. We had heuristics for that too. And then we could scale in a much cheaper way. We could use only 14 processes, Flink processes, rather than I think 200 Python ones. Flink runs on the JVM, so we basically were writing Scala in Java and compiling everything into bytecode. That plays a huge role as well on using less hardware resources. And everything was cheaper because less processes, less hardware, less CPUs. So the entire system was scaling better and it was cheaper. All right, we're hiring, by the way. Yeah, that's about it. I can take a few questions. I think we have 5 minutes.
Yeah, I can just speak up. I wanted to ask, how do you measure the correctness of your ML prediction? So, yes.
It's off, but yeah.
So you talked about the ML confidence and how accurate they are.
Yeah.
So like, how do you measure the recall? Like, are there people who?
Yeah. So.
Like, how do you get the ground truth essentially? Like, or how do you think about it?
Yeah. So we had to. Yeah. It's a good question. We used users. So at Yelp, we have a lot of data from the Yelp app, and we used users check-ins to know when you're actually in a certain restaurant. So that's our gold standard, right? So yeah, when you check in, generally you're doing it while you're there. So we can double check your location, you're checking in, and all the other features at that moment in time. And then by abstracting those features, yeah, you can basically check that your model, what's your model performance, yeah.
You talked about the D, the distance and the time window. Is that learned as well, or?
Is that, sorry?
When you do the clustering over time, do
Yes.
you learn the time windows, or is that a heuristic, or like how do you think about it?
You mean the global window, or?
Yeah, the global window. You had like the less than D.
Oh yeah, so that is just so how do we do that? Yeah, so we were doing everything offline on say you do it on a day of data or on a month of data, and you can pretend you're in a stream. Like you can just select a couple of pings at a time and pretend you're analyzing them pair by pair, and then you do it with different meters distances, and you check which one gives you the best outcome, right? So we were emulating what's happening here. Yeah. Yeah. Hey.
So you mentioned that the original system had some issues regarding the duplication of some push notifications, right? And
yes.
that creating a bad experience. How did you solve that problem later on in the new system?
Yeah. So yes, many various different things. I think our growth team, first of all, they implemented a check on a previous notification. So there was some, if I remember correctly, there was some, how do you call it, run, in Cassandra. They had a problem where that state in Cassandra that I talked before, it was, they were selecting all the recent pings, I think, from Cassandra, and that was their state. And then they were running some kind of worse clustering algorithm, and they were doing the push. But if you get two times the message to do this job, you're selecting twice from Cassandra. What I think they did, if I remember correctly, is they saved some other state in Cassandra to know if they already processed something. So they hacked something on top of it. What we did was, we knew that SQS had this problem, and we wanted to move away from something that had an at-least guarantee. And even though I'm not sure all parts of our pipeline haven't fixed this, it was just much better than what we had before. So there was also a metric that we tracked. It was, I think, it was quite high before, and it was way, way lower after. So there was different teams were tackling the problem in different ways. And I see moving away from SQS as a win in that direction. Because yeah.
Thank you.
Just to get the scale at which your inputs are coming, how many users at a time are pinging you, and with what frequency each user's device is pinging the server?
I sincerely don't remember. I don't know if I could even tell. But more or less, we get pings every few minutes. I don't know. It varies on the time of day. So I know that in the mobile they were doing so many optimization not to drain the battery. So it was very rarely if you don't need to. Like if you're somewhere, we're optimizing for your battery, so it doesn't need to be very often. If you're moving maybe, and then that's when we want to know, should we, provide you this notification, then maybe it was going higher, but definitely don't remember very precise, yeah. What is the scale of the users? I don't know. Yeah, but our system it was in the slide, we are wearing the thousands per second as raw inputs. So, yeah, various thousands. I think, oh yeah, there's also,
in your algorithm, is the distance d variable or static? Or like, is it dynamically changing?
yeah,
or is
good
it like a
question.
static value?
So it's the result of that analysis that we did. So after we found a threshold that we liked, we put it static. But it must be, like, you should run the analysis again and again and change it, but it was static. It was based on an offline analysis that we did on the data that I was telling him before, right? So we ran over a day or a month of data with different D values, and then when you find a nice threshold, we put it statically into the model, but then you keep running that analysis, so it varies over time if it needs to vary.
Okay.
Right? Okay. If it's more or less always the same, we don't change it. Yeah.
Hello, may I ask you, where is the source of the location? Are you guys using the GPS location of the user?
Yeah, latitude and longitude, yes.
Or if the user has already turned off the permission, and you guys use like inaccurate, estimates from like Wi-Fi locations?
No. So you get asked about opting in, and you can choose. So if it's opt out, you don't get the feature, and we do nothing, right? Oh, okay. It's an opt-in, yeah.
Maybe one last question.
So Spark has inbuilt XGBoost support. Why did you choose Flink?
So various reasons. So you mean Spark streaming, right?
Yeah. Why did you go ahead with Flink instead of some other technology, basically?
Yeah. So first of all, we did this a year and a half ago. To do this, so various reasons. I guess you can implement the same thing in various different technologies. But at Yelp, we have chosen Flink for all use cases similar to this, for anything that needs to have low latency and be quasi-real time. And we use Spark for any kind of batch processing. So that's our policy in general. In our case, we obviously consulted with the stream processing team because they know much better. And their response at the time was the Flink had all these features I was talking about that were well tested, that were being used. Like Flink is used by Alibaba, and they do billions of messages per second with Flink. So it was just working at a different scale than sparse streaming with different reliability. Like it was just everything was so much better. Today, I'm not sure that's what that's the consultancy that we got from our stream processing team.
Okay, thank you.
Yeah. Okay.
Thank Luca. Thank you for the great talk. Is this working? Okay. Yeah, it's pretty rare to see wins on both the cost and performance. So pretty awesome work. For the next talk, I'd like to introduce Suchakra. He will be talking about, the topic is pretty interesting, finding stranger things, the lost art of exploring your code. Suchakra is currently a staff scientist at Shift Left, where he plays around with large graphs and hunts bugs. He completed his PhD in computer engineering from École Polytechnique de Montréal, where he worked on eBPF and hardware-resisted tracing techniques to advance systems performance analysis. On related works, he has delivered talks and training at venues such as Usenix Lisa, All Systems Go, Papers We Love, and Tracing Summit. So, cool. Let's welcome.
This is the first slide of my talk.
Okay. Let's welcome Suchakra.
Can you all hear me? Okay, perfect. So this is how the talk will go. We start with like very low expectations. There will be some, good wow effects in between, and then it's gonna like simmer down till the time you sleep. Okay, and when you reach the red zone, just tell me, okay, it's time to like just cut this out. Okay, so finding stranger things, the lost art of exploring your code. This is a big shift from the talk you just saw before, but it is still somewhere in the domain that you can query stuff, you could get content out of it, okay? If you love compilers, you will like this. If you love security, if you love hacking, you will like this as well. Okay, we go down all the way to the code itself and see and some tools and techniques which you can then use to debug your code. Okay, so you know about this already. I love samosas and poutine. I think that was missing from the introductions. Okay, so this is the agenda for today. We'll go through some just basic understanding of how code is structured. We'll see various graphical representations of code that can be done. And we'll move on to code property graph, like how graphs are used when code is actually being developed and compiled, and how you all have been using it like behind, but you never gave it a thought. And then we'll use some tools that we have developed in-house. One is Ocular and the other is Yorn. And then finding some honest mistakes which are there in your code, and some actually not so honest one, the vulnerabilities that some folks have like leached or which are there in the code. So let's look at this small snippet of code, and suddenly I'll annotate this so that everybody gets a refresher of how code looks. Too much info, okay. Okay, we'll go through the top. This is Java code, okay. So the structure is same for something else. I just took Java here. So package or namespace, it defines like what is contained within it. So everything is contained in the package you import in some of the languages. In Python, these are modules. In some other languages, the constructs are something else. But overall, packages or namespaces, they are usually like what it is. Then class or types, because in Java, the types can also be classes like strings. So they themselves are classes. So we'll have like we'll mark them as classes or types, okay? Then the class has some stuff like there's a member variable here. Sometimes in some languages like Java, .NET, there are annotations, special annotations. So these are marked as annotations here. Then there is a method here. So there's a definition of a method getParent, which is here. And this is called as method definition. There's a method block. So I'm just refreshing all of that. You all know this, okay? So if you don't know this, then okay, it's a different story. But this is a method instance. This is different because it's basically a call site of a method. The method is not defined here, but it's an instance of that method here. There's a literal inside it, like a nice string literal. You all must have left a lot of literals in your code. They tell a very horror story sometimes, so we'll look at that. And then the return of the method. So the method runs, and then the method returns something. Sometimes in some languages, for example, here there is private static, so there are modifiers to some of the variables which are there. There can be modifiers to methods as well. Similarly, there can be annotations to method, and like here, the REST controller is an annotation for this class. So now you know what a code is. What we do with code is basically just take it and we compile it, and then it's on some cloud. Nobody cares about it, and we don't know what happened to it. Okay, but actually, like the code gets compiled to some intermediate representation, either runs on a VM, which then, while it is running, compiles it live, which is just-in-time compiling, and compiles it and runs it on the hardware, because it has to run on some hardware. Like low level, there is a CPU which just understands ones and zeros, and some combinations of it, assembly. So, but it runs somewhere. So you compile this and it's gonna run. So anything you leave here is going to affect anywhere it is run. You know, I mean, the cloud is not something actually in the cloud. Okay, it is some servers running your code somewhere, and they can create havoc if you are not careful about how you're coding. So we'll try to dig into that as well. So how code looks and how people have assumed it looks is there's code, and then we compile it, it becomes like some chunk and it runs. Okay, that's how we are perceiving it, and that's the way we analyze it. We take these binaries and try to make sense of it, or we look at our IDEs and try to see, okay, who called who. Like every one of you who is coding here, they know that they always in IDEs go from, okay, all the instances where this method is there. So you keep on jumping. So you think in graphs. Similarly, people who are attacking these infrastructures, they also think in graphs. They move from one point to another point, and they pivot and they move to another point, or they do some lateral movement throughout their infrastructure. So they also think in graph. So everything is actually a graph. But how we'll reach to this to the theory that, yeah, it is actually a graph. And that's how it should be thought about and actually queried for. So the same kind of code which you just saw before would be something like this. There's a class, there's a method which is defined. So Apple class defines foo, which then calls bar. And then it inherits from some class like fruit class, and the bar is then defined in another class, which is a mango class. It inherits from, so you're seeing that there can be a graph, and it's a never-ending graph with nodes as methods, as classes, as the types, and the edges as the relationships between them. So the graph will keep on increasing. And when a compiler actually looks at actual language, they all compile it down, they all work with these relationships between individual components of the text itself. So along with these relationships, we also see that data is also being passed. So there is information, there's a multiple layers of graphs which are already there in the code itself. We just have not exposed it yet. We are just not arguing with that yet. So code as graphs, very complex stuff. Okay. So here's the small piece of code which is on the right-hand side. I hope you like this. This is very simple. Okay, everyone would be able to understand that. And there are some representations during the process of compilation which a lot of compilers use. We don't do that. We basically have created half a compiler where we hack up the stuff which we take from the compilation process, and we do something with it. But before that, let's understand like what are the different pieces that compilers play with when they are compiling this code. So abstract syntax tree. So where the nodes are, where it's basically just a tree. And the nodes are functions, predicate, declarations, conditionals, and then what happens with them. For example, this function is declared. So the declaration says end equal to x, and there's a call to source. So this is basically the first line, which will be translated as. And similarly, a second line. So this would be a representation of an abstract syntax tree, where the whole structure is now represented as a tree, and which the compilers then take on and build something with it. Similarly, there is another information which is there in the same code base, which is control flow, that how the control is flowing, because there are some conditional statements. So something may happen, something may not happen. So a very simple one, there's a true here. It will reach this, the flow will reach through these nodes. Otherwise, if there's a false, it will reach through the other nodes, okay? And then similarly, program dependence graphs, like the hierarchy of the programs, the way they are structured. And as compilers develop some more information, they have other stuff also. We have not put all of the things here, like a dominator tree or other optimization passes that happen in between. So these kind of things also happen. So what happened is that I met this guy called Fabian, and he was doing some research on security. He's a security guy, like total security. Okay, and he said that let's take some components of compilers and put them together and represent the code as a graph. And they actually did that. So Yamaguchi and his friends, Fabian Yamaguchi and his friends, they all created this combined representation of the graph, which we call as code property graph. And we took up his work, and everything kept on like going fine, as it happens in startups. And then we started building this as a fundamental technology on which you could query the code and get insights from it. So this graph becomes like the complete graph with all its relationships, and it has also been enhanced with some more stuff. But this is the fundamental technology on which I will explain to you what we have built further. So now you have a graph with all these relationships from one node to the other node, which has not just information about individual statements, but also operations happening inside them, but then also very high-level information about class hierarchies, or between which method belongs to which class. And if you build a good enough engine, you would be able to actually query all these relationships and navigate your way through it. And that's what we are gonna do. So this is what the graph is. In like it's not, if you don't like the research paper description, then this is a simple version of that. Where at very low level you have information about data flow semantics, control flow, but then as you go above, you have very high level flows which are existing, such as security critical flows. Like we have found out some places which are okay, these can be vulnerabilities, these can be interesting sources and sinks to begin investigations. And then you can go all the way down and navigate through, up and down throughout the graph itself. So I call it the CPG pyramid. Okay, it looks like a pyramid because I just wanted to make it a pyramid. There's a link below. If we have time or if you're interested, we could go down and actually look at like how individual nodes and edges look, and then we'll have some sense of it. So now, how do you work with CPG? The idea is we take an application. Right now, we support like .NET, C, etc. We take this application, we generate this graph, and then once the graph is generated, we have the relationships between each of the nodes and edges inside the graph. Then you could actually query the graph. So in this case, you would try to find if there's an attacker control source here, and then you'll see there's a sink, and then you'll try to find out if a flow exists between them. And if it does, then okay, there can be a vulnerability there, or there can be a bug there. There's a case where somebody left a bug. Similarly, you could do queries on just data flow, data leaks, etc. Like, for example, like I think it's 3 years back, like Twitter had a data leak where some person had left like a log line not in debug, like in production mode, where passwords of like unencrypted passwords of everybody was just flowing directly right into the logs. And you know, like logs are not so secure. Everybody is sharing these logs. They feed into some other things like Kafka, and then people do analytics on them. And so it's not secure. So there was an internal breach that happened. So these kind of things can happen, and they can actually be found out if you have stringent techniques to query whether something is reaching from some source to something. So to explore or aid in exploring this, we have two tools which are there. The one which is below is called as Yarn. It's an open source query engine, and it supports C, C++. You can go on yarn.io and you can see how this graph can then be queried. The other one is a proprietary one. It has a free version for researchers as well, which has a data flow engine as well. It supports C, C++, Java, Scala, etc. There are some investigation recipes or plugins which are already there so that you can actually find out if certain cases were violated. For example, for C, C++ users, for automotive industry, there are some guidelines. So we have cooked up some already interesting recipes and scripts that you can just quickly work with. It comes with an interactive shell. So today we'll be playing with Ocular because it's a little bit more powerful. But the same queries also work in Yarn, which is open source. You can go ahead and start using it or build your own parsers for this big graph. Okay, so let's hunt some bugs in some code. Okay, I'll just give you a quick overview of one bug which we'll try to tackle. So an SQL injection. How many of you know what an SQL injection is? Nice. So, okay, so this is something like that. There's a form, and then there's a request which goes on inside, and somehow deep down inside the code, somebody is actually preparing a statement. Okay, and there is like this. It's basically a query which is directly reaching here to the statement, and then you prepare the statement and you do a query. Okay. So in the case where you could control the parameter directly, which is coming from the query, and you have not sanitized it at all, it may actually just lead to the query becoming true all the time, and then you leak a lot of stuff. Okay, so this is like a very, very simple example of what an SQL injection would look. There would be much more complex cases which are there. So what we'll do is I'll show you some piece of code from some of the examples that I have, and we'll try to see and hunt them using this tool called as Ocular. Okay, so there's this tool called as Tarpit. Okay, and inside this tool there are certain cases. It's basically just a Java servlet tool. Okay, so inside some of these cases, inside some of these files, you will see some endpoints which are there. So for example, it's a Java servlet, so there's a get order status servlet which is there, and it would be something like this that you were seeing, like get order ID or get order status. And on this, you would, and on this, there's a handler for this endpoint for your web app which is there, which is do get. So this is a typical use of how Java servlets work. It's very straightforward. You have an annotation web servlet which defines that what your class will be, which extends the HTTP servlet, and then it has a method do get which handles the query. So which means that if you give anything to get order status, it basically becomes the first parameter of the do get because it handles the get request, and everything else happens inside it. So inside this method, there is something interesting that is happening, and which is actually this. So there is a parameter called as order ID, which is part of the request, and it is like flowing to this order ID string. And eventually this order ID directly goes and gets concatenated to this string. And then it goes to a prepare statement. There should also be an execute query which actually executes this. But since we know that nothing else is happening and it's just like a direct, use of this string which is coming from the request and eventually just directly reaching a prepare statement, there is a possibility of SQL injection happening. So now let's move on to this tool which is called as Ocular. Can you all see this? So what happens is when Ocular runs, it takes a few seconds. And then it shows you this nice shell, like very much, looks like, you're doing something cool. Okay, you can just run this and like, okay, everybody will think you're busy. So now what we'll do is we'll take that servlet var file which we compiled. So that whole servlet example which was there, I just compiled it with a var file. And we'll just directly provide it to Ocular and tell it to generate a graph for us, the code property graph. So it has control R, so it has like reverse eye search as well. Okay, so here the graph was already created, so it just loaded it from its own workspace. You can go and look at workspace, and it tells you how a workspace looks. So I have some graphs which I've already loaded. So this one is like loaded right now. It's true. Okay, and I can just clean all of my workspace. So think of it as an investigative tool where you are now beginning to investigate. So what we can do is there are many things which exist in it, and the most important thing is the object called as CPG. And CPG itself contains the whole graph. And whatever you can do with this, whatever you can do with the graph, you will start with CPG. So let's try to see how many methods are there, like all the methods which are there in the whole program that we just loaded. So you can do method.name. It lists all the names of all the method. And then let's just list them. So there are a lot of methods which are there in the whole program. You can do size. Now it must be reminding you of some kind of language because it's Scala actually. So all the queries that you give for exploring the code is 100% Scala. So you could actually just build your own Scala programs, do analysis on the code, prepare your reports, and save it and do whatnot. So you could also do full name to just get like the complete name of all the methods which are there. You could go ahead and try to filter them by something. So in our case, we'll do get. Okay, and now it lists only the do get methods which are there throughout. So this is kind of like an interesting. So if you have never seen the code and you just get the war file and you just try to load it, so you have the graph with you. Now you can think what to do with the graph. For example, you would know that do gets are usually the places where anything that is handled is coming in. So I'll say, okay, this is an interesting point. Okay, and you see that the first parameter of this is an HTTP servlet request. So okay, maybe the servlet request data comes through this method. So we'll try to see if the data coming on this specific method is reaching some sink or not. Okay, and so since this is Scala, you could actually just do var source, and you'll just say the parameter of this method, make this as a source. Okay, and it makes this parameter of this method as a source. And similarly, you could do sync, where you know that there's prepare or execute or something like that, and that can probably be a sync. So a parameter of attacker controlled method is now our source, and a parameter of something which is to do with SQL, handling of the SQL, either execute query or prepare statement, that is one of our syncs. And we know that there's a source and a sink, and we have created this thing in our mind already now. Now we can see if actually a flow exists between them. So we can do sync.reachable by source and flows. And the moment I do it, I get this big list of 2 instances in my code where a request coming from doGet is actually reaching a prepare statement sync. And all the flows that happen in between them, like how the data is actually being transformed. And even if the data is being transformed from one place to another, we even see it through an operator assignment. Now, this must remind you of the graphs that we were seeing before, where we had AST edges, and we could actually find out how operators were moving. So we have all of this information now, along with the line numbers and everything. This is easy, but the actual data flow of which is happening from a source all the way to a sink. So once you know this information and you have created, this in your mind that, okay, now I can annotate some places in the source and some sinks, and then I'll try to find some flows in between them. You could do a lot of stuff. So in this case, we were able to find out that, yes, there is a possibility of an SQL injection. Go ahead and look at all these files and see what's going on inside, where is the data flowing, and do some stuff with it. So that's the first case that we had. Does it make sense? Yes, no?
So far, what did merging the graphs achieve? So far, you could have done that through just information flow graph.
Yes, this could be done through the data flow graph.
Right.
Okay, but the merging of graph could achieve. I'll come to the next one. So when you'll see operations in between them. So this one was like pure data flow. You could just annotate something and find out a flow between the data. But you could do something more, as you'll see. So here's another example. Okay, so this is also very similar to the one before. So here's a fork bomb. How many of you know what a fork bomb is? Very straightforward stuff. So a process, it forks, keeps on forking itself until everything is exhausted, and then your kernel says and it just shuts down. And it was actually interesting tidbit. I didn't know about that, and somebody told me, so I put it in the title itself. It was in 1970s, somebody actually found this small piece of code in, I think, IBM 360 machine, like encoded in, I don't know what language, maybe like some very old language which used to run on IBM 360. And somebody found that code, and then they said, what? I think it was in Rabbit or something. And then somebody said, what? It's like Wabbit, and they named it Wabbit. You can go ahead and read about what it is. So we'll try to see if we can find a fork bomb. It's also very straightforward. There's nothing interesting as from something before that I had shown. What we'll do here is just try to see if there is an exec somewhere. Okay. And usually what would happen in the case of a fork bomb, which can happen in the case of a fork bomb, is somebody must have added some command which is supposed to be run. Okay, so it must be coming from somewhere. Okay, and if they have added it in the code somewhere, it would be probably a string. So all the strings which are there in your whole code, you could actually just find through literal. And these are actually all the strings that are there in your code. Okay, so what we'll do is we'll just make all of these strings as one of the sources. So all the literals which are there in your code, they are now sources. And we'll make a sync with like exec or something like that. Okay, and this becomes our sync. And then we'll try to find if flows exist. So okay, so I do see some cases where there are some strings which are being passed from a doGet parameter itself. So it clearly says that, okay, there is almost like a literal which is being passed through the doGet. So something is happening in it. and it eventually reaches like a Java runtime exec. So yeah, kind of like scary stuff. So it's not just this demo code. Just by the way, just to tell you, we find this kind of stuff in real code itself. Like some disgruntled employee, they just left something inside. It's like a string which nobody knows what it is, but it's base 64 encoded, and it's being decoded somewhere in between and hidden between a few comments left somewhere. And then you suddenly find out, oh yeah, somebody's decoding it and executing it. And we don't know, like, it's so deep in the code that you would never know, like, what this unrelated piece of exec is doing until you actually find a complete flow from it. Okay, so still the same thing, data flow from a literal to a sync. Something else that is interesting is with C. So I'll switch to C now because like we have done with that. So this is also straightforward. So memory bugs are not so, I mean, they are very dangerous, okay, but they are not essentially security bugs. Like sometimes they may become security bugs, sometimes they may not. If they deny something, yeah, it is a security bug. Otherwise, oh, I left this in the code. I mean, it's just like that. Or I mean, they can be dangerous and your car just crashes. Oh, anything can happen. So memory bugs are specifically like heap-based memory bugs are not so common, but there are some cases where they can become dangerous. So, and I've taken one of these examples because I actually found a research paper that I was reading. I have it open here if you want to take a note of it and want to read it later on. So zero-sized heap allocation vulnerabilities. So what may happen is, in very simple speak and not too geek speak, is there's a malloc and there's a size parameter to a malloc which allocates a memory. If there is an arithmetic operation which is happening on it, there may be a case where the value, you don't know where it's coming from. It may actually just make the size as 0. Okay, so malloc, which has calculated parameters or parameters having arithmetic operations, can become dangerous. So what you should do is try to navigate and look at the flow, what is happening in the code itself. So, or there can be cases where there can be an integer overflow in the calculation. So what you wanted to allocate is not actually what should have been allocated. So you get like low memory being allocated, and then you try to write some stuff to it, and then you get like seg faults, and if you try to access some part of memories. So you may have a lot of issues this way. There are many ways in which this can be exploited. Heap grooming, if you have a structure which contains 2 structures and you try to write something in one member, it overflows to the other member. So you affect the other structure. And then you have tried to read from the other structure in another routine or something, the structure inside the big structure. So there are 2 structures, no padding. You write something on the first one and you overflow to the other one. And then you try to read the other one, you're reading memory which we should not have read. So these kind of crazy attacks are still there. Very few, but they're still there. So so a very simple thing that can be done to diagnose this is try to find if the size parameter, which is passed to a certain malloc in the code, has actually ever had an arithmetic operation. So in this case, you would have to know if there's an arithmetic operation that happened with that. And now your context completely changes from just doing a simple data flow to actually seeing a parameter and seeing if there was an operation done inside the parameter. So I'll try to show you this specific case itself. I think I have the code with me. So I've created a few scenarios. And actually, this was a real case which somebody from the Silicon Valley Fruit Company asked us. Silicon Valley Fruit Company. So they asked us about this, and we had to actually like come up with this solution and try to show them, yeah, you could actually go back and look at this, look at the parameters itself. So the scenario is very straightforward. There's scenario 3. There are multiple mallocs which are happening in this. I'll just explain one of them. So there is a malloc here, and there is A. Now A is getting some information from another place, which is get number. We don't know where it is, so I'm just assuming it's coming from somewhere. And get number has some things inside it, and where it's taking a number, which is again coming from a place we don't know. In this case, it's A to I. It could come from a user input or some other place. And eventually, there's something happening on it, and then it returns the number back to you, and then you try to work with it, or you try to allocate it. So one of the goals could be to just find out parameters of A. Like so how you would approach this is, if you didn't know the code, you would try to find all the places where malloc was ever used. So not the definition, the call sites. Okay, you go to the call sites of all the mallocs, look at the parameters, and then try to do a data flow analysis from any of the source functions that that could have caused it, like attacker control sources, all the way to the parameter of this malloc, and see if an arithmetic operation happened in between it. So this gives you much more power. So the flow now changes. So inside the flow, you can now do something else also. So I'll try to do this example, and I think I have to load this small example. So now that it's loaded, I'll just try to list all the call sites first. So all the methods. Okay, so we do have a lot of them and some Scala stuff. Okay, and so there are mallocs which are obviously happening here. So I'll try to just list some of them. I have a cheat for this. So it actually just looks at the call sites of malloc, creates a map out of this structure, because it's now like a call site structure, call site object that we have. And inside that, we have more information about location and then line numbers, etc. And when you run this, it tells you that in these files at these locations, the malloc call sites are there. Okay, so it's just one way to go a little bit deep and try to investigate. Now, once you know that the call sites are there, what we'll try to do is we'll try to create a sink, which is A to I. And this time, the return of A to I. So A to I is taking something, and then it's returning. So we know that A to I is an example of an attacker control. It can be anything in the code. And if you know that, you could actually try to find out. So we make this as a source, and the malloc, we make malloc as like a sink. So I think it's just directly the same thing. So here the argument of the malloc becomes a sink. Okay, and we just named it argument instead of parameter in this case. So now you could do sync dot reachable by source, but there's a difference now. You could do passes and passes not. So now you could do something like this: sync reachable by source, give me all the flows, and tell me if they pass through multiplication or addition or any operation which is happening. And the moment you do this, it will give you the exact flow which only contains some of this, either addition or multiplication, which is happening inside this. And it gives you that complete flow from your variable, which from your method, which you think it is an attacker control, to the scenario 3, which is basically your place where malloc is happening. Okay, so while this may be interesting, something which is more interesting is, what if you did not know if there is A to I, okay, and you want to actually start navigating it from the call site itself. So for that, I have another query which is there. Let's remove this thing. So what's happening is we just get the call site, called as malloc. We filter it with this line number. We already know there were a few places of malloc. So as an investigator, I would try to look at few of them and see. So I look at the first one of them. You could also just not do this, and it will give you a list of all of them. And then I do another thing, which is repeat. So what this will do is it will find the previous CFG node, in the control flow graph, it will find the previous CFG node for which is actually where the call out is happening. So the call site, before the call site, what is happening? Before that, what is happening? Before that, what is happening? And it will keep on giving all of those places. And now I map it and get the code, the location, and the line number, etc. So this is all the information I want after I keep on going behind. You could also do a repeat and then until, if you want to stop, until certain condition is met. So you have all these constructs to navigate. So here it tells us that in this line, there was get number that it found out, and eventually it was A. Which was basically where the value came from. So this way you're able to navigate the graph above and find out where the values are coming from. Okay, so I think I'm done with this, and I don't have anything else to show you unless you want me to keep on investigating code all night. I can do that. You can give me your code. I will never say no to any code. Okay, and then we can keep on investigating. Otherwise, if you have questions, please just ask me right now. Yes.
How do you combine the syntax tree, the flow graph to a CPG?
To the whole complete unit.
Yeah.
So okay. Now that you have asked this, I have to show this. There is a small spec which is there, here. In the link, I'll give you the slides. And this exactly tells you how the schema of the graph is. And it tells you what are the individual structures which are there. So for example, the top level is the program structure, which contains the file, namespace, and all of that information. And these are individual nodes. They are joined by AST edges inside each of them. And then type declarations, how they are joined with each of the other nodes. So every individual component is a node, and they are joined with others with edges. And sometimes those edges are AST, sometimes those edges are something very exquisite that we internally have. If you read through it, you will find out. So type declarations are connected via this, and as you go down deep, there would be methods, and inside method, there would be statements and everything. So for example, method instance, and then there's a call. So a call site is a call. So you can keep on going and keep on looking at what all information is there in each of the edges. And if you have questions, you can always ask me.
Okay, thank you.
So with Ocular, you typically look at compiled languages. What's the difference in generating these graphs when you're looking at an interpreted language instead, such as Python?
So this is language agnostic. So for example, Java, it can also be non-compiled, and you could just provide. So for example, with .NET, which runs on CLR and the other runtimes which are there, we just take in code, and then code is just passed directly and represented. Same with C. So with C, we are just taking raw code, and it's not compiled code which we provide with this. So it was just raw code, and we just take it and we represent it in the graph. So because some constructs in all the languages are same, so they can always be mapped with this intermediate representation. In the realm of compilers, think of this CPG as one IR which exists.
All right. And have you ever run Ocular on Ocular to create ocularception?
Yeah, okay. So internally, Ocular comprises, it's written actually in Java. So we can dog food this. So Java and a mix of Scala. And we also support Scala now as a source, so it also works on that. Not completely Ocular, because Ocular comprises of a lot of internal paths. So we have run a few paths with Ocular itself and tried to find some cases where some things are, but I didn't find it. I mean, maybe there are some cases, I'm sure.
It seems like this tool is meant to run once like the code is written and it's production and it's in production and you want to find vulnerability. Is it also can be used during the development mode, like to maybe some integration with IDE or
Yes.
as a CI
So,
step?
good question. So we don't have like ID integration directly. There may be some tools which are there which allow you to do certain kind of analysis, like Coverity is there for C, and so these tools have, some tools have ID integration already. There's FindSec Bugs, I think, which already has integrations, but they work a little bit differently. Like they have few recipes which are made and they run through them and they give you a report. No, very less interactive like investigation. But it can be extended. Right now it is not, but yes, it could be integrated. Yeah.
Yeah, I like the interaction, the way you can interact with the tool itself. So basically, this is a static analysis tool, right?
Yeah.
So it comes with the limitations of the static analysis tool, I assume, like a lot of false positive and a large code base, especially in C and C++, where you have global variables, and dealing with lambda functions and function pointers. Are those constraints?
So lambdas are not constraints. We support them. Like with Java, we were able to just do that. What happened? I would just like to take one step back and explain to you like how it is not a traditional static analysis tool. We do come with a set of certain recipes which we run, and they go through the graph and give you results. Okay, but they don't. But it also provides you the power to write your own analysis, and whatever I was writing, you could make them as scripts, and then you can just run those scripts directly. So this reduces false positives, because this was a big issue. I totally understand, like having false positives. Like some of our customers have come to us and they have said that they run some specific tool, and it ran overnight for like 1.5 days sometimes, and it gave them 10,000 results. That's crap. I mean, a human cannot go through those 10,000 and try to understand that. Okay, so what needs to be done, and why our whole company is named as Shift Left, is actually move towards developers, empower them so that they write their own rules as they are developing, or a security team which is there, they write their own rules as they are developing, and those rules become the actual set. So the way it is there, I'll show you some examples. Like in this case, the engine that automatically runs and actually generates some already predefined vulnerabilities which are there. Wait, hold on. Yeah, so I've not shown one part of the tool to you because I don't want to sell this here. If you want to buy, it's okay. But one part of the tool which is there is called as finding. And this finding contains not all, but some of our own scripts which are running inside it. And then it gives you like a summary of all of these findings which are there. So if you do, I'll give you a pretty printed version, so it's a little bit easy. So for example, here it tells you that there's a command injection already, an RC which is there. It tells you it starts from here, exits here. What we did was actually an actual query which we ran in the demo, but all of these have already been seeded inside and they give us this information. We don't go through normal patterns and look for those patterns. We only look for exact cases where the data might flow in and it might flow out. So basically,
just one more question then. Given what's the lead time of how much setup time a developer needs to be able to find these, write their own recipes, fine tune them to reduce the false positive? Like how much time does that take to get set up generally on an average?
Okay, for Ocular itself, it's just one small distribution is Java. So you just need JVM, unzip a zip file, start with a shell script. That's it. And then you have the shell and you interact with it. The lead time to actually understand and find out, we have provided some pointers. For example, cpg.sources, source.method.name.l, for example, is a simple example of an attack surface where these are all possible sources which are there. You'll see do get being repeated a lot of time. And all of these places are potential sources. And similarly, we have potential sinks. So you could start investigating with them and then creating your own recipes. And there's a list of all recipes which are already there. Some are public, some are internal, which people are using.
One last question. Okay, I guess I'll ask it. So how scalable is it? Can it run on Linux kernel?
Oh yeah, good question, very good question. So we ran early versions of this on Linux kernel, and we found 18 CVEs.
Woohoo.
And we filed them, but as you know, nobody actually acknowledges them. So they just quietly went on as patches, and Linus Torvalds just looked at them, merged, and then it was over. So, but we found 18. They are listed also in either this research paper or the next one, which is coming up. And so right now it took almost 3 hours or something for the whole kernel. We have massively scaled. It's beyond any other graph. So we have our own graphs which are there based on Gremlin Scala. So our own implementations, and some part of that the maintainers are upstreaming slowly.
Cool. Okay, thanks, Suchakra. Yeah, I'm very happy that you guys came. If you want to give a talk at our future events, or if you would like to host us in your organization, do reach out to me or Ria. And I hope to see you again in our next event. Thank you.